Hello everyone. In today's session of CCNA series, I will discuss one of the important QoS tool, that is classification and marking. Classification involves identifying different types of traffic flows such as uh, VoIP, video streaming and web browsing, and then classify those packets based on header content such as source destination IP address, port numbers, and other layer 3 or layer 4 information. And then mark this message by changing some bits in specific header fields. And once it is marked, it can act using QoS tools such as queuing, shaping, policing, and so on. Let's take an example. What a router does, or what is the internal processing done by the router. So when a packet arrives, the router makes a forwarding decision. It uses classification logic to determine which packet will enter which output queue. So here the classification is very important. And once the classification is done, it holds the packet in the output queue, waiting for the outgoing interface to be available to send the next message. And at last, the queuing tool scheduling logic uh, chooses the next packet, effectively prioritizing one packet over the other. So this is the high level overview of what queues, tools do and all. We'll discuss about queuing, scheduling in upcoming sessions. So with classification done, so what marking does is marking involves assigning a specific value or tag to packet based on their classification. Like void packet will be marked with yellow. I mean, it will mark with value in real. Here, if you see, video streaming is marked with different color, web browsing is marked with different color, and so on. So it classifies and marks the packet. So QoS tool changes in marking. QoS tool changes one or more fields, setting a value in the header. So this marking is used by the network devices such as routers or switches to apply QoS policies. For example, packet belonging to the high priority traffic class might be marked with a certain value, while a packet with lower priority class might be marked with different value. Let's take an example here. A PC on the left sending an IP packet to a remote host. Switch 1 does some comparison and mark the packet DSCP field, a 6-bit field in the IP header meant for QoS marking. The upcoming devices that processes the message, that is switch 2, R1 and R2, then use simpler matching to classify the packet by comparing the packet's DSCP value. Placing packets with one DSCP value in class 1 and another with DSCP value in class 2. So this is how it does the marking. Now we know what is classification and marking. Let's see how router performs classification using ACLs and NBAR, also known as network-based application recognition. These are the two types, or you can say mechanism, which can be used for classification. Starting with ACL, ACL are used to control the traffic that is allowed to pass through a router interface. They can classify traffic based on source IP, destination IP, protocol, port number, etc. So ACL can be used to permit or deny traffic based on those criteria. So for any packet matched by the ACL with permit action, consider that packet a match for QoS. So do a particular QoS action. Then, but however, not every classification can be made by matching with an ACL. In more challenging cases, for example, Cisco NBAR can be used. So NBAR is a feature that allows a router to classify traffic based on the application or protocol being used. Unlike ACLs, which typically classify traffic based on IP header information, NBAR can identify uh, application itself, even if they use dynamic port numbers or are encrypted. Let's take an example of NBAR here. With the use of keywords on the left, if you see, uh, you can match the following. For example, entertainment video from Amazon, or video from sports channels such as ESPN. If you look at the first two highlighted entries in the output, without NBAR, it would be difficult to classify an entertainment video from an Amazon versus the video from security camera. But those two highlighted entries show you how easily they have classified the traffic differently using NBAR. So this is also one of the important tools. Next, let's see how this marking is done. What values are used? First, we'll see marking of the IP header. Marking a QoS field in the IP header works well with the QoS because the IP header exists for the entire trip of the packet journey from source host to the destination host. So IPv4 defines a type of service byte in the IPv4 header. The original RFC 791 defined a 3-bit precedence 3-bit IP precedence or IPP field for QoS marking, which is limited to only 8 values to mark. So later, RFC 2474 defined a 3-bit IP precedence, defined a toss byte with DSCP field. DSCP increased the number of marking bits to 6 bits, that is 64 unique values that you can mark. So it increased the numbers from 3-bit to 6-bit, that is from 8 to 64 values. So IPv6 also has a similar field to mark as well, and it is called IPv6 traffic class byte. In IPv4 it is a type of service, and IPv6 is a traffic class. So let's also look at marking of the Ethernet COS or class of service, you can say, or you can say Ethernet marking of the Ethernet 802.1q header. In Ethernet network, quality of service marking in the 802.1q header involves setting the PCP or priority code point field within the VLAN tag. This field sits in the third byte of the 4-byte 802.1q header as a 3-bit field supplying 8 possible values to mark. It goes by two different names actually. Class of service or COS, or PCP or priority code point. QoS tool can make the use of QoS field only for QoS features enable on interfaces that use trunking. If you see, the QoS in Ethernet network can be applied only on the interfaces where trunking has been enabled. For example, if the PC on the left were to send data to a server somewhere, off the right, the DSCP field would exist for the entire trip. However, the COS field would exist over the two trunks only, and would be useful mainly on 4 interfaces noted with narrow lines. If you see the gray lines, so other marking field also exist in other headers such as TID for Wi-Fi and EXP for MPLS. With this, let's move on to another topic, that is defining trust boundaries. This is one of the important topic in QoS. In QoS, a trust boundary refers to the demarcation point. Demarcation point within a network where the traffic is classified, marked, and subjected to QoS policies. So it is a point in the path of the packet flowing through the network at which the networking devices can trust the current QoS markings. You can set up an end user device also to mark the DHCP field, and even the QoS field if trunking is used on the link. But it would be inappropriate if we do so, because a PC user would know about diffserv and DHCP to know that most voice traffic is marked with DHCP called EF, which we will discuss later, which has a decimal value of 46. So voice traffic gets great QoS treatment because of this value. So PC user could mark all the traffic with this value to get a better QoS treatment, which is not what we are intended to. So it is important to widely choose where to place the trust boundary for your network. And that boundary typically sits in a device under the control of the network admin. I mean, the area in which you have the control. For example, a typical trust boundary could be set by the first ingress switch in your network, or if your access layer includes an IP phone, the phone is typically the trust boundary instead of the switch. So IP phones, because IP phones can set the QoS and DHCP fields of the messages created by the phone as well, and as these are forwarded from the PC to the phone. Let's look at different diffserv suggested marking values. Differentiated services or diffserv is a technique used in the network to provide quality of service in modern IP network. It is based on the concept of DSCP, differentiated services code point in the IP header. And some of the commonly used DSCP values are uh, expedite forwarding, assured forwarding, and class selector, also known as EF, AF, and CS. So let's go ahead and see briefly at each of those DSCP values, starting with expedite forwarding. Defined in diffserv framework, provides actually uh, low loss, low jitter, and assured bandwidth for certain traffic classes. So when this value is applied to a packet, it offers low loss, low latency, low jitter, and assured bandwidth for your packet. It is typically used for real-time delay-sensitive traffic such as voice and VoIP and video conferencing. In the IP header, EF traffic is marked with DHCP value of 46, which tells network devices to prioritize this traffic over the other. If you see, there are two tunnels. This is how it is sending the packets when you have a packet marked with EF. It is typically deployed in network where strict SLAs for delay and jitter are required, ensuring that critical real-time application receive the necessary network resources to function properly. The next one we have is assured forwarding. It is a type of quality of service mechanism used in network to prioritize and manage the delivery of packets based on their importance or the level of service required. It defines the concept of four separate queues or classes in queuing system, like AF1, AF2, AF3, AF4. Each of it has its own priority level. This allows the network administrator to differentiate uh, between this different type of traffic and assign appropriate level of service. It also defines three levels: low, medium, and high of drop priority within each queues or class for use with congestion avoidance tools. With 4 queues and 3 drop priorities classes per queue, it offers 12 different DSCP markings, one for each combination of queue and drop priority. So assured forwarding defines the specific AF DSCP text name and equivalent decimal name. The text name follows a format of AFXY, with X referring to Q1 through 4 and Y referring to the drop priority, that is 1 to 3. For example, if you receive a packet marked with those AF1X, all go into one queue. And if you get the packet marked with AF2X, it would go into another queue and so on. Inside the queue, with all the AF1Y traffic, every class is treated differently in regard to drop actions, with one AF11 getting the best treatment and AF13 the worst treatment of that queue because uh, of the drop priority. The following are recommended baseline marking with DSCP assured forwarding per hop behavior. For interactive video, it's better to mark with AF41. For mission critical data, it's AF31. For transactional data, it's AF21. And for bulk data, it's AF11, and so on. Let's move on to the other tool, that is class selector. Class selector is a set of DSCP values that are used to provide backward compatibility with IP precedence field, or you can say older QoS models. CS values range from CS0 to CS7 and are mapped to specific DSCP values, allowing network that use IP precedence to be integrated with modern DevServ network. So this helps you to have a backward compatibility with the old QoS model. Here, the CSX represents the text name, where X is the matching IP precedence value, that is 0 to 7. So this is why this class selector is used. Now with so many different, so many diff serve marking, an engineer might get confused about how to implement it on different types of network or different types of network in your traffic. For that, Cisco has come up with RFC 4954, which simplifies and recommendation on how to use these DSCP values. It tells how all devices should mark the data. Like for voice payload, mark it with DSCP EF. For interactive video, mark it with AF4X, for example, video conferencing. And for streaming video, mark it with CS4. For high priority data, low latency data, that mark it with AF2X. And for standard data, mark it with CS0. That's it for this session. I hope this was informative for you. Thank you for watching. If you have any query, please do contact me. I'll be more than happy to help you.